Day 152, Honors Physics, Magnetic Forces on Charged Particles. And I can start off right away by saying the only time there's a magnetic force on a charged particle is when the charged particle is moving in the magnetic field. I'll come back to that. So you might want to put that at the top of the page. Now, there's going to be a lot of visualization here once again. We've got to visualize things that are invisible, so to speak. We have to conceptualize what these things are. So it's theater of the mind. You're not visualizing imaginary things. These are things that exist. Magnetic fields exist, but they're invisible, and they're three-dimensional. So we have a challenge here. So let me go back to the page, top of the page, or let me review one thing, and that is, where do magnetic fields come from? They come from the movement of a charged particle. 99% of the time we're talking about moving electrons or spinning electrons. Now we have two things that are going to be going on, so we've got to put a lot of things together. And there's a lot of geometry here that we've got to think about and then write on it and symbolize on a two-dimensional piece of paper. And there's a lot of international conventions that are helpful, but need a lot of practice to get these figured out. So we'll start off with the equation here at the top, and then I'll explain it. Okay, so I wrote a lot of things down here, so you will probably want to pause this for a minute and then write these down. Looking over here on the right-hand side, there's multiplication. When you multiply numbers, the answer is called a product. In other words, 2 times 3 equals 6. 6 is the product. We're multiplying 2 times 3. There's different ways to symbolize multiplication, more so than anything else. You know, when you add two things, you have to put the plus sign. Subtract, you have to put the minus sign. Division, there's a couple symbols for that. But multiplication, there's 4 or maybe 5 ways to symbolize that. But like this little x here, it's not an x, it's times. 2 times 3 is 6. But 2 times that, 2 with a dot, 2.3 means 2 times 3 is 6. Or if you make 2 in parentheses times 3, that means times 3 equals 6. Those are mathematical conventions that you all understand. Down here, this is 6 times a squared. And that a squared means a times a. So there's a lot of ways to symbolize multiplication. Well, over here, we're going to get really specific now. This is an equation. Let me put it in a box. This equation here is the equation that we use, and I can put a subscript here, F sub m. It's magnetic force. It's the magnetic force on a moving charged particle when they're moving in a magnetic field. This x right here, where the blue arrow is pointing, means multiplication. In math and physics, it's what we call a cross product. It's a special kind of multiplication. So there's different kinds of multiplication. Maybe you've heard that before, maybe you haven't. What it means is, once again, you might want to pause this. What it means, a cross product means you have to introduce another part to the equation. That is the sine of the angle. Cross product means take the sine of the angle. Now, what angle are we talking about? Well, it's the angle between two of the vectors. In this case, the angle between the vector v, the velocity, which has a direction, and the vector b, which is the magnetic field, which has a direction. So this angle here is the angle between two vectors. Now, basically all the problems we'll be doing this year is that angle will be 90 degrees. Well, if you remember from trig, or you can plug it in right now, sine of 90 is a right angle, sine of 90 is 1, so this will almost never come into play for us this year. This will always be sine of 90, it'll be 1, so we stop writing it after a while, and we end up just writing F sub m, magnetic force is QVB, where Q is the charge of the particle, V is the velocity with which it's moving. If the velocity is 0, there's no magnetic force. The force, once again, over here, it's measured in newtons. Charge is measured in coulombs. Capital C is the symbol for coulombs. The velocity we want in meters per second. And the magnetic field strength, once again, will come out in Teslas. Another conceptual thing to think about is, why is there a force on the magnetic charge? And here's a basic explanation for that. Most magnetic fields are linear in a sense, and that's what we're going to be dealing with here. For example, the Earth's magnetic field Now it has curvature to it, but in a localized small region, like at the room we're sitting in, like if we're sitting in my physics room, the the magnetic field due to the Earth is pretty uniform. It's all pointing towards the north, towards the front of the room, my smartboard. It's linear and it's even. You put a compass anywhere in the room you're sitting in, even the room you're sitting in now at home, the compass will always point in one direction, towards the north. So it'll always be very uniform. It'll always be the 4.5 times 10 to the negative fifth Teslas. It'll be that size and that strength no matter where in the room, and it's all pointing north, the same direction. It's not curving much. It's insignificant, the curvature to the magnetic field in your room. It's a constant uniform magnetic field in one direction. So the electron, when it travels through that room, as it travels, has a circular magnetic field. That has a bunch of directions, tangential to the circle of the magnetic field as it circles around that electron. And that hence gives rise to these forces, because magnetic fields like to be lined up. North and south poles like to be attracted, two north poles repel, but the magnetic field around an electron doesn't really have poles. It has a direction. It's either clockwise or counterclockwise, but you can simplify that into a direction, tangential direction at any point in time, or any point in that circle, and that direction, whatever direction that tangent points, is north to south poles, if their poles existed there, which they sort of do if you use that convention. But bottom line is, the force exists because the charged particle has a magnetic field that's circular, trying to go through a linear magnetic field, and it creates a force that's perpendicular to its motion. Now, we're going to use what we call the right-hand rule. And we have to think of three-dimensional space. If we go down here to the bottom, you don't have this on your page, but you can visualize this. This is the XYZ coordinate plane. I think these are German. I don't know if it's German or what, but horizontal, longitudinal, vertical, I don't know. The three-dimensional XYZ plane. So you have to envision that all three of these directions, X, Y, and Z, are perpendicular to each other. It's like the corner of a room, but we have to solve problems, and we have to have a handy device. Well, handy, your hand will be your device. So I'm kind of going to do this backwards, and I'll do it forward, and then we'll do a bunch of practice problems, because once you get used to these, they're fairly straightforward, but it takes a lot of visualization, especially the first few times you do these. So in the equation at the top here, there are three vectors, and the vectors all have directions. There's a magnetic force, which has a direction, the velocity has a direction, and the magnetic field has a direction. The charge Q does not have a direction. That's just a scalar. It's like 1.6 times 10 to the negative 19th coulombs, whatever charge you have. Usually it's an electron or proton, but it doesn't have to be. It could be a little particle that has a bunch of electrons on it, an ion of some sort. Anyway, going back down here to the right-hand rule, the three fingers, well, one's a thumb, you're going to use your right hand, not your left hand. And if you look these up online, sometimes they switch these around. It doesn't really matter which one's X, Y, and Z, or F, Q, and B, F, V, and B, I should say. It doesn't matter technically which one is which, as long as you're consistent. But you want to get your hand in that configuration. Otherwise, you take your pointer finger, your index finger, and point it. And I'm going to do this with my finger in the direction of the current, the flow of the current, or the movement of the charge, I should say. So this one says current, but it's the movement of the charge. Let me put that on there. So your finger will be the direction, pointing in the direction that the electron or proton. Well, we're going to start with protons, because the convention is with protons. We have to make a little adjustment with electrons. We'll come back to that. But this is the motion. So it's like, so your index finger and your thumb are like, when you make a gun with a gun, like when you were a kid, and you curled your other three fingers into your palm, and you had your index finger be the the direction you're shooting, and your thumb was like, you use that for the trigger or whatever. But your thumb and your index finger, are at right angles to each other. So there's a right angle right here. Then you take, and it's a little bit awkward, you take your middle finger. I call it your bad finger, and B for bad, well, B is magnetic field, but it's going to be perpendicular. That has to point perpendicular to your palm. It's kind of like, you know, when somebody flips you off, to be kind of crude about it, that's how that finger, it's perpendicular to the other two fingers. I make a joke in class, never use that finger in isolation, because it's crude. No good. Anyway, so you have your three fingers. Put them in that orientation. These three fingers are the X, Y, and Z. It doesn't really matter which one's X, Y, and Z. What's important is that they're all three perpendicular to each other. They're three mutually perpendicular vectors, just like the X, Y, and Z directions if you were to graph three things in the three-dimensional space. When I do these, I always use my thumb as the force direction, my index finger as the velocity direction, and B, my bad finger, as the magnetic field. You can change them all around, but that's the way I'm going to do it, so my answers will be consistent with that. There's other methods, but this will work. Once again, like we learned the other day, these symbols here, I just drew them in, an X, the circle's not that important. It's the X, but the circle kind of contains the X. X means towards the floor, dot means towards the ceiling. It's very important. That gives us our three dimensions. So basically X is like left and right, Y is this way, towards the top of the page and bottom of the page, and then Z is towards the ceiling or towards the floor, and these two will represent the Z direction for us. So I'm going to give you some examples, and to some degree, it's going to be difficult as we start, but then once you get going, there's really almost a 50-50 chance you can get the right answer, even if you don't kind of know what you're doing. So I'll explain that as I go along here. So let me give you some sample problems, and then we'll do an actual calculation problem. All right, so I have three example problems that I drew out. So this is an example problem here. I'm actually going to start with number 2. When your diagrams are done, every diagram will have a circle, which is going to represent towards the ceiling or towards the floor. In this case, I don't know if it's ceiling. I don't know if I have to put an X in there or a dot in there. That's what I'm going to explain to you. And then two vectors that are perpendicular. Every diagram is going to look like this when you're done. This can be labeled differently, and this may have an X or a dot. That's all that's possible in here, an X or a dot. There's going to be three letters. There are three vectors. There's the force vector, the magnetic force, from that equation up in the upper left, and the velocity. What's missing here in this problem, there's three vectors. There's F, there's V, and there's B. The vector B, the magnetic field, is missing. That's what's going to go by this. So we're looking for the direction of the B field, the magnetic field. I can label that. I'm going to use a different color. I'll use red. So I'm looking for B in this case. The question is the magnetic field towards the floor or towards the ceiling? So if you don't know what you're doing here, you have a 50-50 chance of getting the problem right. So I know the answer is either an X or a dot, but you want to get it right. Let's practice this, get it right. So what you have to do right now is get your right hand out, and you have to point your index finger toward the left. That velocity vector points towards the left, and you have to have your thumb, which is your force vector, always the force vector, has to point towards the bottom of this page, which is basically towards your body. And if you do that, your index finger automatically points towards the floor. So we know the answer here, if you use the right-hand rule, first time through it, is an X. So that's the red X is the answer. Okay, number 1. I'm going back to number 1. What's missing in number 1 is, once again, B, my B vector. So I'm looking for B once again, my magnetic field direction. I have two possible answers. Okay, because there's always a circle with an X, but I have that. It's my velocity now. The proton, let's say, is moving towards the floor. Okay, these are done by convention with protons. We'll come back to electrons in a few minutes here. And my force is to the right. What I'm missing is my magnetic field. The answer's got to be either this way, up towards the top of the page, or down this way, because that's the only two ways that are perpendicular to F. So I have one of two choices, and I could guess my way to the answer, but I don't want to do that. So the answer is either pointing towards the bottom of the page or top of the page. But what you do is you get your right hand out, and you have your index finger, so that's the velocity vector, has to point towards the floor. So your index finger has to point towards the floor, and your thumb has to point towards the right. Now, it's kind of awkward to get your hand to turn that way, but your thumb has to point towards the right of the page. Your index finger has to point towards the floor, and if you have your hand with your three fingers, like it's shown in this diagram down here, your middle finger, your bad finger, automatically in that case points this way. So that's your answer. Number 3 on the right. All right, so what we're missing here is the velocity. We have F and B. So there's always three vectors: the force, the magnetic field, and then the velocity. So I already know that the answer is either going to be to the right or to the left if I have a proton. So which way is it? Once again, you just get your right hand out, make sure you have all three fingers perpendicular like the diagram, like this. And in this case, you want your bad finger pointing towards the ceiling, because that dot means towards the ceiling. You might need to turn your whole body or the whole page, whatever works for you. But and this is really hard to do with your body sitting in a chair facing forward, because your bad finger has to point towards the ceiling, and if I put my right hand with my actually outstretched to my right, and my thumb points toward the back of the room, parallel to the floor, and my bad finger points towards the ceiling, my index finger automatically points to the right. So the answer for this one is to the right. So my velocity is to the right. That's my answer. So you're looking for the third vector. Given any two, you can find the third using the right-hand rule. Now, one caveat here. If this problem had told you it was an electron, because these are all conventionally with protons, if it was an electron, the answer would be the answer would be opposite of what that red arrow was. It would be pointing to the left. I'll come back to that. So you have to remember to reverse your answer. Like, for example, in the middle one here, if it said in this middle problem here that the problem was dealing with an electron, that answer would have been a dot. Or here, if it said you were dealing with an electron, the answer would have been down to the bottom of the page. So you assume it's a proton unless they tell you it's an electron. Let's practice a little bit more here with the problem at the bottom of the page. Okay, so a little background here. This basically is how they operate out at like Fermilab, when they used to have real experiments at Fermilab, and now they have a particle accelerator out in Switzerland or France. It's called CERN. It's where they use magnets to steer charged particles, because they can force them into circular motion, as you'll see here in a few seconds. So this is the basic math behind how they steer protons and electrons and then smash them into each other. But they have to be charged particles, because you can only get a force on a charged moving particle. You can accelerate them linearly with electric fields, which we're not doing right now. We'll do that in a little bit. But you can accelerate them or force them into a circle, centripetal acceleration, circular acceleration, with magnetic forces. So here we have a charged particle traveling south. In part A, it's a proton. So we're going to draw the diagram here. It tells you the numbers, and we're going to plug these things in. But we're going to draw the diagram first, if you read the whole problem. So the diagram is always going to have a circle. So I draw my circle. This is part A for the proton. So this is a charged particle. The proton is traveling south. Now on a piece of paper, south is towards the bottom of the page. So what I have is my velocity is towards the bottom of the page, so I can label that. That's V. It experiences a force that's to the east. East is to the right. That's the conventional direction for a force. So I have F. So the question is, what is the magnetic field? Well, the magnetic field either has to be towards the floor or towards the ceiling. So what I'm missing is B. That's what I'm looking for as far as the direction. I'm also going to get the size of that. But we're going to use the right-hand rule to figure out the direction of B. So we'll do that again. It's another practice problem here. So let's get our fingers ready. So our index finger has to point towards the bottom of this page. It's kind of hard to do. You might have to turn your body. And your thumb has to point towards the right. So basically, if you turn around in your chair and your thumb points to the right and your index finger points towards the bottom of this page, your middle finger, your bad finger, points, I'll change colors here, to the floor. So that's an X. That's my direction. The magnetic field has to be towards the floor. Uniform magnetic field towards the floor will cause this motion. Now it says, calculate the magnitude of the magnetic force. Okay, so we're just going to plug into the equation. The equation is F equals QVB sine theta. Theta is 90 degrees. So we just plug in. I'll do that. So I wrote this all out. They gave us the force. Make sure they're in newtons. And this is the charge of the proton. You have to remember that or look that up. I can remember it. You'll remember it as well eventually. 1.6 times 10 to the negative 19th coulombs, and the velocity in meters per second. If you plug those all in, just plug and chug at this point, it comes out to be 1.25 Teslas. All right. Now in part B, and then the direction is in the diagram. As long as you have the diagram there, it's towards the floor. So B is towards the floor. You can say it again if you want to, toward floor. All right, but the diagram will do it for me. In part B, you have an electron. And what happens in part B is if you look at it, well, once again, if you look at the diagram, you have the same force, and you have a velocity this way, and it's asking you to get B. Well, it seems like the same problem, and it basically is, except for, as I mentioned a few minutes ago, it's an electron now, and sometimes in the diagrams on a test, I'll put like a minus here. That means the velocity of an electron. If it's a proton, I put nothing. So in part A here, it was assumed to be, well, it was a proton. I don't put a plus up here, but V negative means it's an electron. So if I do the right-hand rule, like I did in part A, that means it would be an X towards the floor. But with an electron, you just reverse your answer. You could use your left hand. I don't recommend that. I just reverse my answer. But bottom line is the answer for the direction would be a dot towards the ceiling. And if you go to the math, it's the same math. It's the same force. Electrons have the same charge as protons. They're different mass, but they still have the 1.6, so it's still the same answer. It's going to be the same mass, so it's just going to be B equals 1.25 Teslas, but it is toward the ceiling. Or sky. Part C now, the radius. A little bit trickier. So what magnetic forces do is they deflect particles, charged particles, into circular motion. It is a centripetal force. It causes the electron or proton to go into circular motion because it's not pushing from behind or slowing it down from the front. It pushes it from the side and just turns them. So bottom line is in part C, and we'll do a few practice problems on this, the centripetal force, F sub C, is the magnetic force, F sub M. Let me do a little better job there. That's F sub M. Well, you have to dig back into your bag of tricks, so you can look it up. The centripetal force from first semester is a force towards the center of circular motion. And the equation for F sub C was F sub C is mv squared over r. I don't expect you to remember that. And as we're doing right now, the magnetic force is qvb sine of 90. So there's your math. That's the magnetic force is a centripetal force, mv squared over r, and there's the mathematical setup. And we're looking for the radius. If you do the math here, move things around, the radius, what you'll find out is one of the v's cancel. The radius is going to be mv, if you do the algebra, over qb. You just plug those numbers in because they're all given. Well, they're actually not given. It says, you need to know the mass. And we'll just do it for the electron because they will have different radii because they have different masses. They have the same velocity, the same charge, the same magnetic field here, but I happen to remember the mass of an electron. I'll plug it in. So I just plugged the numbers in. I knew the mass of the electron is 9.11 times 10 to the negative 31st kilograms. You want that in kilograms. And the velocity was given 2 times 10 to the 7th. Once again, you need to know the charge of the electron and the magnetic field. I guess that's a strong magnetic field that results in a pretty small radius. If you repeated the calculation for a proton, basically it would be about, the radius would be about 2,000 times bigger because the only thing that would change is that the mass of the proton is almost 2,000 times bigger than this number. So you multiply that number, it's like 1,800 or something like that. You could plug the number for the mass of the proton in there to figure out the radius, and it'd be a much bigger radius compared to this one, almost 2,000 times bigger. But there you go. Magnetic forces deflect moving charged particles into circular motion. They create a centripetal force causing circular motion on the part of the electron or proton or any charged particle moving through a uniform magnetic field. We're assuming all our magnetic fields are uniform. and everything is going to be at right angles and all the problems that we do this year.